Okay, so now let's say we want to look we want to get the same curve, but this time with a different approach that we call replication. So let me share with you my whiteboard. So the way we did it in the past in the first case was we had our x-axis, y-axis, and x-axis. And so basically we said the y-axis is the strength, the x-axis is the temperature, and we did some measurements that we called the randomization measurement. So we got one here, one here, one here, one there, one there, one there, one there, one there. And so we assigned to we fitted a curve to all of them, which we said it goes like that. And one of the reasons that they didn't fall exactly on this curve, on our true curve that we called it, and we don't have access, by the way, in a real experiment, is that these are not done for the same temperature, the same duration, I'm sorry. So for instance, this guy, there's a difference here. There's a difference here between this and that's because this guy is done at, let's say, t equal to 1 hour, whereas this other guy is done at t equal to, let's say, 2 hours, whereas this guy is done at t equal to 5 hours, something like this. Okay, so the times are randomly distributed around 3 hours. This is what we call the randomization. Now, an alternative, and so in this case, I have about 10 experiments done. Now I want to show you a costlier way of doing it, which is a more reliable way of doing it. And that is where we control time and temperature both. Still keep basically time at temperature at the core of the experiment. So in this case, we are dealing with, again, we are dealing with the y-axis and the x-axis. Here we are measuring temperature. Here we are measuring the strength. And in all of these cases, at each data point, at each temperature that we want to run the experiment, we set a very narrow range for time. Let's say we say the time is, let's say, 3 hours plus minus, let's say, 5 minutes. That we can control it very well. At each point, we repeat the experiment. So we make multiple samples at this temperature, whatever that is. Let's say this is 100 C. We repeat the experiment. We make multiple samples at this temperature. And we repeat the experiments like that. Okay. And we and then we go. Let me do it this way. We get multiple measurements here. Then we go to the next point and we say, let's say there's another temperature here, whatever that temperature is. And let's say in this case, the temperature is 150 C. And in this case, we get some other values. And then we go to another case, which is, let's say 200 degrees. And and we do again the measurements. And so now we can much more reliably fit a line to all of these measurements and call this our trend. As a matter of fact, the way we represent this data is not necessarily with these showing the individual data points. At each of these measurements, we report a strength, the average value of a strength, plus standard deviation of the strength. And the way we show it is with a very, very genius, smart way of showing it, which has a lot of good data in it. So the way we show it is that we say this is the average and this is the one standard deviation. This is the average and this is the one standard deviation. This is the average and this is one standard deviation. This is sigma, this is temperature. And these are all on, and then in this plot we say time of curing is 3 hours plus minus 10 or 5 minutes. And we fit a curve to the average values. We fit a curve to the average values like that. So now, what you realize is that in this case, at each of these data points, I did the experiments maybe 5, 10 times or something, and I have 5, 10 different conditions. So the number of experiments I'm running is way more than the, in this replication method that I'm replicating each test at very well-defined, narrowly defined conditions. The number of experiments is many times more than the randomization method. So it improves the precision of my measurements drastically. Oops. And it decreases the variance because in this process, in the randomization process, the time of curing was 3 hours plus minus 2 hours. Whereas in the replication method, the time of the curing is 3 hours plus minus 5 minutes. So although the time of curing is less important than the temperature of curing, the duration of curing is less important than temperature of curing, it still has some effect. And we see those effects, unfortunately, in the randomization process. So that's the cost of the randomization process. Whereas the money you pay to do the randomization experiments is far less. Now, when you do the replication method, you can also estimate the error because you can calculate the standard deviation. And so now, how is that replication, how that error is important? Well, now when you go back to this whiteboard, you see a difference between, for instance, this measurement and here. This is the difference between these two. And it happened, let's say, from 100 to 150. How is this difference much more than this standard deviation or more than this standard deviation? Or is this error within the difference between the error bars? So for instance, is it something like this? Or it is that one is much larger than the other, even when you consider standard deviations? Or is it like that? In this case, although the average of the second point is slightly higher, but the standard deviations are so large that you can say within statistical uncertainties, these two parameters are the same. Whereas here you can say within a statistical uncertainties, these, by considering statistical uncertainties, this value is larger than this value. So, and so in each case, you do the replications and you report the average. So here, the order really doesn't matter. You have to do all the experiments and you have to average them. So I'm going to stop this video and we're going to continue next.